So welcome to the AI and Big Data in Finance webinar. We're delighted to have two distinguished speakers today. My colleague Asaf Manela from WashU Olin will present his paper on time-consistent large language models. And Suproteem Sarkar from Harvard University will be the discussant. Now, Asaf will have 30 minutes for his presentation, and then Suproteem will be discussing for 20 minutes, and probably about 15 minutes in, I'll be pausing for some clarification questions. And we'll also have Asaf's co-authors in the audience who can probably respond to questions in the chat as they come up. And then after the discussion, we'll open the floor for broader questions from the audience. So please submit your questions in the Q&A, and I will then call on you during the questioning part. And just as a canonical reminder, please be respectful with your comments. The presentation and discussion will be recorded and will be posted together with the slides on our website. And after the main part of the webinar, we'll have an unrecorded discussion where we'll upgrade everyone to a panelist, and we'll hopefully have an exciting exchange of ideas. So without further ado, Asaf, the floor is yours.
All right, thanks for having me. I've been looking forward to presenting at this wonderful forum, so much appreciated. Let me try and share my slides here. Give me a thumbs up maybe if you see slides. Yes, all right, thanks. So this paper is joint work with Songrun, Linying, and Jimmy, all of whom are excellent finance PhD students at WashU. You should look for them in the upcoming rookie market, no doubt. So LLMs are cool. I don't need to convince you of that. And as researchers, we all want to use them. The thing is that they are trained on recent data, which introduces lookahead bias. For example, if I show you a model that had the 2015 edition of Gray Sports Almanac here in the picture in its training data, you may find its ability to win sports bets in the 1950s somewhat suspect, right? So in finance, we are particularly sensitive to lookahead bias because many empirical tests rests on the efficient markets hypothesis. How can we rely on the ChatGPTs and the Claudes of the world, which are continuously fine-tuned on human feedback and can search? Our solution is somewhat straightforward. I promised Mariam that in 5 minutes you'll understand the whole paper. This is it. So what we do in the paper is we train two families of chronologically consistent LLMs exclusively on preceding text. So this is something I think that's very natural to somebody in finance. We do this all the time, just not at that scale. So what we do is we create chrono variants of two very popular architectures for LLMs. The first is BERT. BERT is a workhorse model developed by Google in 2018. And in fact, an interesting historical turning point when language models started beating the average human's ability in language understanding. Tip of the hat to Leah Stern and the panelist who gave me a tip about BERT back in 2018. The other architecture is GPT-2, which is the last open source model released by OpenAI. So we aim for two such variants, and for each series we have models from the year 1999 all the way through 2024. The main difference between them is that BERT is trained to fill in masked words in a sequence of words, like a clause problem, while GPT is an autoregressive model that is trained to predict the next word in a sequence always. But you don't have to choose really, because we've posted both model families on Hugging Face, and you can now download their chronologically consistent versions. So this sounds simple, right? I think the hard part, we realized, is training such models to be competitive with larger models, which have much, much more data available for their training. And I'll explain more about how we do just that. But before going there, let me preview our findings. We find that ChronoBERT and ChronoGPT exhibit superior language understanding relative to similar sized models and comparable performance to much larger Llama 3.1 models. In an asset pricing application of predicting next day stock returns from financial news, we find that ChronoBERT's Sharpe ratio of 4.8 is comparable to state-of-the-art. That's a word that depreciates very, very quickly in this space, but is comparable to Llama, whose Sharpe ratio is 4.9. And the fact that the difference is so small means that there is only modest look-ahead bias in this particular setting. Now, this is not a theorem. It doesn't say that look-ahead bias doesn't matter anywhere. It just says that this is the fact. This is the case in our application. But there is, in fact, recent evidence by Levy and by Lopez, Lira, Tang, and Zhu that look-ahead bias may be more severe in earnings data, for example. So that's that's an empirical open question whether these chronologically consistent models can do just as well in other settings. The literature on look-ahead bias with LLMs is growing very rapidly because, again, we all want to use them, but we are very much aware that there's look-ahead bias in them. And my discussant, Suproteem, made a very important early contributions in explaining how look-ahead bias arises in these settings and what we can and cannot do to overcome them. We make two contributions, I think, to this literature. The first is to develop and publicly release LLMs that are free from look-ahead bias and simultaneously capable of high-level language comprehension. And this really, the end that is the hard part, I think. We hope that in doing so, we can sort of pay the fixed cost of estimating these models and that social scientists will find them useful for research. The second is that we use these models to quantify look-ahead bias in the news return predictability application and find that it is fairly modest. So now that you know what we do, let me turn to how we do it. The training LLMs is usually split into two stages. This is a jargon, so let me clarify this jargon so we're all on the same page. There's a pre-training stage, and in pre-training the model learns to predict missing words in text sequences. So imagine taking large sequences of text and masking or hiding a particular word there, and then training a model that's aimed to fill and predict what that missing word or token, really it's parts of words, is. This is really the computationally and data hungry part of training LLMs. The second stage of it, fine-tuning, is when the model is further trained for specific applications like chat or Q&A or reasoning, or even predicting next day returns. What we do is we pre-train ChronoBERT subscript T and ChronoGPT T only on text available before time T. So for example, web pages that are crawled in 2005 would be used for pre-training ChronoBERT 2005 using ChronoBERT 2004 as a sort of hot starting point. Now, ensuring that these models are competitive with much larger counterparts poses two challenges. The first is limited compute. So if you've been paying attention, I don't know, research funding is drying up. I'm very skeptical that we can, get the compute resources of the OpenAIs and the Anthropics and the Googles of the world. So we are very limited in that regard. But even if we could overcome that compute hurdle, we are still limited in the fact that we are limited to historical data. And if you've ever seen a plot of knowledge or text created by society, over the years, that's an exponential curve. So if we now limit ourselves to say data pre-1999, we are substantially narrowing the amount of text that we can use for training our model. Now what's playing for us is that there's been a lot of work on making pre-training LLMs more efficient. This is part of the reason the API costs of using them fell by several orders of magnitude since ChatGPT came out a couple of years ago. So what we do is we select diverse, high-quality data, carefully filtered by publication date, to maximize information gained from our limited corpus. We also train over multiple epochs to maximize learning from the available corpus. Our initial 1999 models, that's the first vintage that we felt had enough data for us to go out with, they are trained on about 7 billion tokens over multiple epochs. And this multiple epochs means you're taking the model multiple times through the data, but because there's stochastic gradient descent somewhere in there, doesn't mean that you're really duplicating the all of the observations. We should not be surprised that the model improves with multiple epochs. The second thing we do is, once we have those 1999 models that we really invested a lot in, we do incremental training from 2000 to 2024 and generate a model snapshot every year in December on a corpus of 65 billion tokens altogether from 2000 to 2024. Okay, so this is the amount of data that we brought to bear to the point where we thought these models are worth writing home about. But we start by squeezing every bit of juice out of our pre-1999 data. We train ChronoBERT 1999, that's what I'm showing you here, the accuracy in red and cross entropy in blue. And we train ChronoBERT 1999 on just enough tokens until its language understanding, which I'm showing you here on the right side, is as good as the original BERT. So the original BERT is this dashed red line here. And BERT had an advantage in the sense that Google had data all the way up to 2018 to train it. So we can get to roughly the same spot in language understanding based only on 1999 data. We similarly train ChronoGPT 1999 on enough tokens until its language understanding, shown on the right, is as good as GPT-2. There's a slightly different evaluation metric common for autoregressive or GPT type models. Here we use HelloSwag, which is a commonly used benchmark. Once we have these 1999 models, we use them as starting points for training models from 2000 to 2024. Here you can see the x-axis is the vintage of each of these models. And you can see how these models improve in their language understanding over the years. Now, you'd expect this curve to somewhat increase as we're showing more text to the model. You'd expect its language understanding to be better. It's not, dramatically different between 1999 and 2024. Although, if you squint quite a bit, you can see an increasing curve fitted to that. And here is what that curve looks like for ChronoGPT models. ChronoGPT models actually see, somewhat of a larger, over a steeper curve over the years. Although, again, in magnitude, I don't know if that's such a big difference. In this table, we report the size, the context, and the knowledge cutoff for ChronoBERT and ChronoGPT, and for several benchmark models. Our models are similar in size to BERT, to FinBERT, that's trained only in financial text, or more on financial text, to GPT-2. In terms of the number of parameters, they're fairly similar, although our models have larger context windows. This is part of the sort of more modern architectures for these models. In the next slides, I also benchmark against the much larger Llama 3.1 with 8 billion parameters released by Meta. Its knowledge cutoff is December 2023, right? So the comparison is going to be between these chronologically consistent models and the much larger Llama models or BERT that is chronologically inconsistent. But I should not, skip Suproteem Stories LM model, which beat us by, just a few months in releasing one chronologically consistent series of models. Stories LM, I think, is a family of models. I should have put this as a family, but its last model, if I remember correctly, has a knowledge cutoff of December 1963. So I will also compare to that model. All right, so GLUE is a commonly used suite of NLP benchmarks. And ChronoBERT, you can see here at the bottom, attains a GLUE average score around 85, while ChronoGPT gets scores around 75. I want you to try and remember these numbers, 85 and 75, as I switch to the next chart with the other benchmark models. So Llama 3.1 attains GLUE of 86.3. BERT, the original BERT by Google, is at about 85. FinBERT is at 76, and Stories LM at just under 80. So my conclusion from this is that ChronoBERT and ChronoGPT exhibit superior language understanding relative to similar sized models, and one that is surprisingly comparable to the much larger Llama models.
Asaf, I think it looks like there are no questions in the Q&A, so maybe just keep going, and as questions come in, I'm sure Songrun and Jimmy and Lingying will be able to tackle them as we go along.
Sounds good. This is a very simple paper, I told you. So now I want to take a step back and acknowledge that there could be errors even in our chronologically consistent models, in the sense that we're curating our training data to include data which we believe is available by a certain date, but this doesn't mean this process is perfect. For example, if we look at a publication date that was OCR'd, then there could be mistakes in that process, and we're open to that and we're upfront about that. So for example, if there is a publication date that is actually, I don't know, say 2009, and the OCR makes it to like 100 years earlier, then our models could still have some traces of look-ahead bias. What I'll next show you is a few sentence completion exercises where a chronologically consistent model, as we call them, should do well on facts within its knowledge cutoff and poorly on future information. So for example, I'll start by asking ChronoBERT to fill in sentences like these, where we supply the year and year +1, and we ask it to fill in which president was inaugurated in the next year subsequent to a US presidential election, right? So you could all solve this problem very easily, but you're standing in 2025. Suppose you were standing in 2020. How well would you be able to solve this problem? So I'm going to show you a few charts like these. If you have better ideas on how to present them, they're welcome. But the way we've done it is that the stuff in blue is a correct prediction by the model. The shaded words, like those here, are words that are outside the model's knowledge cutoff. So for example, BERT was trained on data until 2018. So 2020 and 2024 elections are shaded because these are outside of its knowledge cutoff. So a good chrono model should have all blue outside of the shaded region here and all black in the shaded region, right? I hope that was clear enough. It took me 5 minutes to understand, what's going on in these charts first time. Maybe hopefully you're faster than I am. So what we find is that ChronoBERT knows only what it should about US presidential elections. The only exception here, if you look at the shaded region here for the ChronoBERT models, is that our model actually, our 2020 model actually predicts Trump's re-election in 2024. You may ask yourself, well, how could it possibly do that? So it's possible that we have a super intelligent model. It is more likely that it's just, looking at who's the last president in its training set and projecting forward. All right. We then tried a bunch of other salient facts, like the Enron scandal in 2001. So if you ask, if you give it this masking problem, mask forward problem, in 2001, the Enron precipitated the passage of the Sarbanes-Oxley Act of 2002. Then before 2002, it guesses amendment, and after that, it guesses scandal. That's sort of how it's supposed to work. We tried the SARS pandemic of 2003. We tried the subprime mortgage crisis of 2008, the Brexit referendum of 2016, the coronavirus pandemic of 2020, and the AI wonder that is ChatGPT back in 2022. Right? So if you prompt something GPT, mark the major milestone for generative AI, it has no clue what the hell you're talking about up until 2024. All right. So we take this as evidence that we don't find any evidence of Lookahead bias in any of these tests. And that's this 0 out of 76. And actually pretty accurate prediction within the knowledge cutoff. So 72 out of 80, which are correct. All right, so armed with our chronologically consistent models, we can quantify now the importance of Lookahead bias in the news return prediction application, which is sort of close to, I don't know, our hearts as asset pricers. So for each firm day observation, what we do is we use an LLM, either the chrono versions or the inconsistent versions like Llama, to embed the set of headlines into a numerical vector representation. Jargon for this is embeddings. So we create these embeddings using different LLMs, and we then fit a regularized Fama-Macbeth regression to map news embeddings E to return predictions R. Now, I should say we are not innovating in this step at all. We literally took what Chen, Kelly, and Xu did in their recent papers on using LLMs for this problem. And all that we wanted to do was sort of replicate their exercise, but use chronologically consistent LLMs and compare their performance to the much larger Llama type models and to other benchmarks. So Chen, Kelly, and Xu were careful, and so were we, to not introduce further look-ahead bias. And so to not introduce further look-ahead bias, we estimate these regressions on the preceding month's data, okay, asset pricing and news data and embeddings data, to get the coefficients, the betas, and then we then use those coefficient estimates to form out-of-sample news-based return predictions, R hats. We then take these R hats and form and sort stocks into deciles of expected returns. And then what I'm going to show you on the next slide is basically long-short portfolios on these decile portfolios. Make sense? I hope. So here we report results for our real-time predictions with ChronoBERT and ChronoGPT and compare them to those of much larger and inconsistent from a chronological standpoint, Llama 3.1. If you focus on the last line, you can see that remarkably, we find that ChronoBERT performs almost as well as Llama. This is Llama's Sharpe ratio. This is ChronoBERT's Sharpe ratio, both in terms of mean excess return and the Sharpe ratio that I showed you. So a 61 relative to 60, almost 6. If we compare ChronoGPT to that, we see that ChronoGPT does not do as well on this task, though its performance is still quite impressive. Now, the fact that ChronoBERT can come so close tells us that lookahead bias is fairly modest in this particular application. Okay, lookahead bias sort of needs to live between this Sharpe ratio of 4.8 and 4.9. All right, so here's how other variants of BERT perform on the same task. We see that BERT, which is chronologically inconsistent, attains a lower Sharpe ratio. FinBERT, which was trained on more financial data, does not do so well. And Stories LM, which was carefully constructed not to include data after 1963, does similarly. Now, these are sort of statements asking you to compare point estimates. We run formal statistical tests and find that indeed ChronoBERT is comparable to state-of-the-art and inconsistent Llama. So we cannot reject that their Sharpe ratios are the same, but you can reject that most other models get very different Sharpe ratios than Llama. Now, there's an interesting question as to what's going on. Like, is it the fact that we use up-to-date knowledge that, or that we train the model for better language understanding? So to gauge the importance of up-to-date knowledge, we report Sharpe ratios for different vintage models. So what am I showing you here in this graph? The dashed blue line is ChronoBERT real time, what I just showed you before in the table, where we always use the most recent vintage model of ChronoBERT. By contrast, each point on the solid line, for example, let's say the 2004 point on the solid line, this shows the performance of the same trading strategy, but where we use ChronoBERT 2024, just this model, to embed all news. Okay, so some of this is lookahead bias, some of this is that it has better information. But what you can see from this chart is that there's somewhat of a pretty modest improvement over model vintages. And we would expect somewhat of an improvement. But again, I don't think this improvement is that dramatic. Now, this can come from two sources. It can come from the fact that, well, up-to-date knowledge is not that important. It can also come from the fact that BERT is still a relatively small LLM. So it could be that if we had a massively larger LLM, it could remember many more facts, and then you would see a much steeper curve here. In fact, we don't see a similar improvement from ChronoGPT. And again, I think it's possible that this model is too small to remember the facts. And we're working right now on scaling it up and hope to report results pretty soon. All right, so what have we learned? We learned that training LLMs without lookahead bias is super easy. For example, if you trained a model that just predicts Asaf all the time, that model would have zero lookahead bias. And you say, well, great. But training chronologically consistent LLMs to understand language well enough to be useful, that we learned is actually pretty hard. So we hope to save the profession this fixed cost. So we released ChronoBERT and ChronoGPT on Hugging Face, and we hope you'll find them useful. In terms of the economic message of the paper and sort of the finance asset pricing space is that in the news return prediction setting, lookahead bias appears to be relatively modest. But again, your mileage may vary, So we encourage researchers to try chrono models in other applications and to quantify lookahead bias there. Now, before I turn you to Sarkar, I wanted to plug in a different approach. So you may think, well, your models are way too dumb for me, compared to ChatGPTs of the world and to Anthropic, and I'm very open to that. It's kind of remarkable that we can attain the same levels of asset pricing prediction as Llama. So in very complementary work with Joey, Will, and Luca, we think we think a lot about how to take text that may give the LLM hints about, and traces of look-ahead bias, and mask those terms. We call this entity neutering. And so what we do is we remove identifying clues by using the LLM against itself. Okay, that's how I think about it. Where we instruct the LLM to replace names, dates, products, etc., with generic tokens. And we show that unlike, I don't know, simpler ways of masking that have been documented in the past, this proves quite effective in removing, in neutering the text, in the sense that the LLM cannot recognize the firm. It cannot recognize the time in which news comes out, and allows us to avoid, to a large degree, look-ahead bias in our estimates of return prediction. So I'm not going to spend more time on this one. I just wanted to throw the idea out there. These papers are both online, and I encourage you to check them out. All right.
All right.
This is all for me.
Thank you so
And
much.
I'll turn it off on to Suproteem. I thank you for discussing our paper, and I look forward to your comments.
Well, thanks so much for this fantastic talk, Asaf. And now we'll hand it over to Suproteem. We're excited for your discussion.
Now I'm not muted. Thank you so much for inviting me, and thank you so much for an amazing and very interesting paper, Asaf. So I'm happy to talk a little about the paper. I think the engineering contributions to the paper are very cool. But let me start by just giving a bit of background, just to kind of rehash the problem of look-ahead bias and how some of these sort of time subscript models or chronologically consistent models might address it. So let me go back to what Asaf mentioned with pre-training, right? So pre-training is a way to expose language models or other types of models to diverse sources of historical data, right? In the language setting, this gives language models information about how language is structured, right? Like how do words come together? How do concepts link together? In addition, this pre-training corpus gives models information about events embedded in the data. Suppose you have a headline that the World War is over or that Kennedy was slain on Dallas Street, right? These are information about historical events that are also embedded in the data used to train language models. Now, in forecasting analysis, some information must not enter in, right? We have an information set, a desired information set. We don't want information from, that's not that information set entering into forecasting analysis. So to make this a little bit more explicit, right? Suppose we train a model on historical news data, right? There's direct information if we're forecasting stock prices, for example, right? IBM stock price might be mentioned in the historical data at a period after a forecasting window. There's also indirect information, right? Suppose IBM's business model has changed. It's discussed similarly to consulting firms now. Its multiple is more like that of a consulting firm now. That also induces an association in the representation space of the model that can introduce this information leakage into any forecasting task. Right, so as we mentioned, in forecasting, some of this information must not enter into analysis. And in asset pricing and macro forecasting and other domains with forecasting, researchers are already careful not to include data X from after the information cutoff, right? We know that can leak information and lead to overstated claims of performance. Now that folks are starting to use these pre-trained models, it also is worth pointing out that these pre-trained models F can introduce such information from after the information cutoff. Right, and such information from pre-training can make forecasts that involve language models invalid. Right, suppose we have a statement that a model trained on information about historical events can forecast historical events. How can we interpret such a statement? So let me introduce a little bit of formalism, just one example. Right, so this is an example that Kian and I showed in our paper, Look Ahead, Bias, and Pre-trained Language Models. Right, we take an earnings call of Zoom. we prompt the model to forecast risks, considering only information up to and including the earnings call, right? Despite such an instruction, when we actually generate those risks, we get things like the COVID-19 pandemic and the shift to remote work that are unlikely to be in the information set, or at least have high probability at that time. Right? COVID-19 wasn't a phrase that wasn't invented at that time, right? More broadly, there's evidence across a host of domains of look-ahead bias from pre-trained models, right? Paul and Caden have this nice paper showing out returns. Kian and I show it for language sequences and election winners. I show it in my job market paper with presidential completion, and Bradford shows it for earnings announcements and earnings growth, right? So there's a whole host of evidence that suggests that these types of models can induce information that shouldn't be in the information set when we should be doing forecasting exercises. So a bit of formalism, right? The goal of a forecasting exercise is to forecast some outcome yt plus 1 from some language xt, restricting to a desired information set it. So this then can help us to define an object that we can call the irreducible error, right? What can we not predict using the information available up to time t, right? All contained in it about the outcome y. Now, what is an LLM? It's a function that takes in language x and is parameterized by some parameters m induced by the pre-training data and optimization procedure, right? And information leakage with these models can occur when the information induced by these parameters is not contained in the information set of interest. So suppose now our research takes an LLM and builds some predictive model mu hat, right? So F is the LLM output, G is some analysis procedure that lives on top of the LLM output parameterized by theta. This can help us to define look-ahead bias. This is when the irreducible error is correlated with the output of the researcher's predictive model, right? And traditionally, we might think about look-ahead bias about some correlation between the theta of the analysis procedure and the irreducible error, right? We're training some model on historical information that sneaks into parameters that we then use to forecast future information. In addition, the look-ahead bias from pre-training is also, an analogous, type of issue that enters in, right? It's not models that we have usually trained ourselves as researchers, but these are parameters that contain historical information that can enter into the analysis procedure. And by just treating kind of the output fx conditional on m as data, we risk kind of missing out on this important introduction of this information from pre-training. Right, so how do we address this problem? This idea that parameters from these language models might contain information that we shouldn't be using in forecasting. One approach that has been proposed is changing the language itself. So masking, I think, is a broad name for these procedures, which is removing information from xt to form some xt masked, some way to remove things like firm names, time markers, products, and so on. Right, and what's the implicit goal of this procedure? It's to try and mask x enough so the correlation between kind of the forecast and the irreducible error reaches 0. And how can we do this? One way, as I've mentioned, is to just degenerate to a constant, right? Just output one thing all the time, right? Then you're not going to have look-ahead bias. We're not going to have a particularly useful predictive model. You could also achieve this if masking just happens to counteract leakage, but it's hard to understand, in what domains we can censor enough information about X that it won't inappropriately pair with some information M in the language model to look ahead, right? And the idea here is like, do we just want to trust intuition when we're doing this? Right, we know that machine learning can reconstruct labels from degraded data. There's this nice paper that shows this in the context of medical images, where radiologists can extract a signal. They think that the image has been corrupted enough, but a machine can, right? So how do we know that the data has been corrupted enough? And I think that's led to some issues with interpretation of this, both because it reduces information, and two, we're still not sure about the guarantees on a whole host of problems and how much this will actually avoid the look-ahead potential. But what is likely to address the problem, what will address the problem, is changing F, the language model, actually using models with pre-training data from before the information cutoff, right? Gemini is training information up to the present, which contains information about things like COVID or the global financial crisis, right? But why don't we use a language model only trained on information up to a particular point in time, right? This might get us closer to our desired goal, where there's no correlation with the irreducible error. And one way to do this is through these historical LLMs that folks have released. There's also a way to do this in a way that might be more real time through what Kian and I call LLMs with time subscripts. So there's Stories LM that I released a few months ago. Bradford Levy has a model that he's about to release. I think these are models that could help researchers kind of address this problem by guaranteeing that there's no kind of leakage, because there is no data that is either from or selected from a window after the forecasting period. So what does this paper do? It's an awesome way to kind of do this task of changing F, right? Actually building a series of language models using time subscripts. So using continual learning, they'll train two families of models, ChronoBERT and ChronoGPT, and they'll find first that these models perform well on standard language benchmarks relative to their peers. In addition, when we look at the outputs of these models, they find evidence consistent with no information leakage when the model is trained up to the desired knowledge cutoff. And finally, they find similar return forecasting performance for their own models as well as other models. So let me just briefly recap the paper. I think Asaf did a great job going through it, right? There's these two model families. One is mass language modeling, it's an encoder model. The other is causal language modeling for generation. They train a base model in 1999 and further train on each year until 2024, right? And they also try to filter the pre-trained data with high scores on a classifier that has been shown to kind of produce sometimes higher quality documents. So visually, they're going to take this data up until 1999, they're going to use that to produce that first vintage of the model. Then they're going to roll forward that model. So they're going to keep the parameters from the last one and then introduce data from 2000 and so on, and produce this family of models on this data with the property that suppose the data is well curated and not selected based on current information, that's a data set that's going to guarantee you have no leakage for information about the future. Now, what do they do with the model? The first way they do it, the thing they do is they try to validate its performance on language benchmarks, right? So they find that ChronoBERT performs comparably to BERT and Llama 3.1 on the GLUE benchmark, which is a collection of many language tasks. Notably, it's awesome that this model performs better than FinBERT and Story's LMV1. I really am glad that kind of we're getting better and better at language understanding with these families of chronologically consistent language models. They then use the model and try to verify that their pre-training data is kind of well cut off, right? Well specified. And they show that it does indeed seem to be the case that models trained up to information up to a particular point in time don't leak information about the future, which is a great way to kind of validate this time subscript chronological consistent nature. What they then do is they then turn to a return forecasting exercise, right? Basically what they're doing here is they're finding directions in an embedding space that forecast returns. So let me try to explain this in a picture. They're going to take a bunch of headlines or concatenated headlines for each day for a firm and put them into ChronoBERT or other models and construct some embeddings in an embedding space. What they'll then do is they'll learn some regression. I'll just do a plain classification so it's easier to visualize, but learn some regression of returns on sort of embeddings using past data, right? And they're very careful to have good data hygiene here, as we've emailed back and forth about. Right, so the idea is like you're going to learn some way to take this embedding and produce some signal. They then take that signal, construct a portfolio sort, and then form some statistic, right? We have this model, we have this embedding, we've historically learned the relationship between embeddings and returns. Now let's apply that to today's embeddings and try to forecast tomorrow's returns. Now, with this, they find pretty similar performance to some comparable models, and even better performance than some peer models, and also somewhat comparable performance to some other sort of contemporary models like Llama 3.1. This suggests that kind of there's good performance of these models. I'll send the authors the slides on some more benchmarking they could do there. Now, what I want to talk a little bit about is the interpretation of this exercise, right? I think the statement that look-ahead bias is modest is quite a big claim, and it's not clear to me how, as researchers, one can support that claim beyond a specific research design, right? Even if you think about news for return prediction, there are differences in architecture, data, the forecasting procedure, the pre-training corpus that are all parts of a particular research design when you compare losses across models. And I think more broadly as a profession, it's important for us to take an adversarial perspective on look-ahead bias, right? Asset pricing research transforms data in many ways, right? Suppose you have modest differences in return predictability in one domain. Researchers have pretty poor intuition, but in general, folks seem to have poor intuition for LLM performance generalization. What's the guarantee that if you have modest performance in one domain, you won't have very good performance, sufficiently good performance in a different domain? So to make that a bit explicit, let me talk a little bit about the research design. Let me talk about kind of how it might map onto another sort of caricature of this type of argument, right? So suppose someone comes to you and says, hey, I constructed a trading strategy using data up to the present about my sorting variable, or real-time data, right, only up to the forecasting period about my sorting variable. And I found that portfolio A and portfolio B had similar performance. Therefore, I can claim that no trading strategy that uses data up to the present has look-ahead bias, right? What makes us read this claim and feel a little uneasy, right? One, what is the sorting variable, right? Maybe it was the first letter of the firm name. Maybe it was the book equity of the firm, right? We might have some intuition that future book equity is kind of informative of changes in future valuations, right? So we might have intuitions on which sorting variables are less appropriate, but as a field, asset pricing has kind of excised kind of the idea that we can be, choosy about what things we're okay having look ahead with, and has instead really tried to use real-time data, right? We've really kind of gone against this idea of using any information about the future, right? Folks I've talked to at hedge funds, mentioned the fact that forecasting is inherently low signal, and any look-ahead potential could swamp out true signal in a forecasting analysis. Right, so kind of to make this idea explicit about how research designs could vary across different researchers trying to approach the same task of headlines to forecast returns, right? Let's go back to the research design in the paper and talk about how other researchers might modify it. right? There's choices of the model, there's choices of the data, and there's choices of the analysis procedure. Let's start with the model. So as Asaf mentioned, right, this is a smallish model compared to the frontier right now, right? It's probably one of the largest models that has this property of being time subscripted, but it is a smaller model. And there is evidence in other domains, both by Paul and Caden and by Bradford, that there are differences in forecastability around pre-training cutoffs for models larger than this, both for returns and for earnings growth, right? After a model doesn't know about contemporaneous events, forecasting returns or forecasting earnings growth has become harder for some of these larger models in their particular research designs, right? So to understand how that could kind of modify the interpretation here, right? Suppose we use GPT-5 whenever it comes out to embed headlines, right? What might happen? Things might move around the embedding space, right? There's more scope for information to leak in. And again, you have this kind of very modern information with a very expressive model class. This moves around the embedding space. Even if you are very good with data hygiene and forming the classifier of, buy versus sell, the fact that the embedding space has been moved around by this model trained in the future and this very rich model means that you still have this potential for that future information polluting the statistic you eventually learn, right? So the idea that the representation space may change as you change the model induces different types of memorization that create concerns. Let's go to the choice of data X, right? So news headlines are informative, but they are also limited in content, right? So Kian and I show that more content and input data can also leak more information, right? Obviously, you can take an adversarial approach to try and censor the data more and more, but still you might find that more information leaks more and could produce signals that are more consistent with look-ahead bias, right? So suppose you use ChronoBERT to embed all contemporaneous news language available over all outlets, full text using some clever aggregation procedure, right? Again, what happens there is you're moving around the locations of the embeddings of the forecasted firms in the space, right? Even if your decision boundary is green, it's good, it's found using good data practices, the pre-training procedure with a lot more information in the data you use could also change the embeddings, which would help you reconstruct signals that you otherwise might not, right? So the choice of data is very important to our research design. Finally, the choice of analysis procedure, I think here there's just immense variation in ways that people are applying language models to the setting, right? So in the author's setting and the papers that they're kind of building on, right, they're forming some classifier based off some representation of contemporaneous news, right? Folks are also using models to ask questions, right? Is this firm going to be affected by the pandemic, right? We know that discussions of pandemics changed. Is this firm overvalued? Again, we think that those discussions may change as valuations are realized or changes in valuation are realized, right? So there's a lot of room to move around, even in the analysis procedure, holding the model fixed and holding the data fixed, right? So you could just draw a decision boundary based off past returns. You could also draw some kind of representation of decision boundary with the pandemic question or with the overvalued question or with any other question, which again creates arbitrary maps from language into signals. Just because one particular research design doesn't appear to leak more doesn't mean that everyone will. So again, this may lead arbitrary information to enter the analysis. So I just want to make this point explicit. I think that as we think about look-ahead bias, it's important to build kind of mental models of in which cases its potential may increase or decrease. And there's just a lot of design choices in trying to figure out, in any researcher's kind of decision to kind of apply these models that I think we need to understand the flexibility of. So I just want to use this to make the point that look-ahead potential need not be uniform across research designs, even for the same researching task. So let me just try to give you one example with the current model and kind of the current data, kind of how you might think about just reconstructing a research design in a way that could leak information about the future. So let me go back. I mentioned this before, right? Like in low predictive environments, look at good drowned out signal. So let me go back to what the authors showed, right? On the right, there was this kind of thing with the presidential last names. On the left, there was this kind of figure about Enron and kind of what happened with Enron. And again, you see something different in the generated language, which suggests a difference in the association and the ways that firms relate to one another in the representation space, depending on the vintage of the model. What does that mean? Right now, when you have two different representations for the same language, depending on the vintage of the model, that is like precisely something about information from the future changing the way the embedding space is formed, right? So suppose you form a trading strategy where you're trying to bet against like overhyped stocks and you build some classifier, not of kind of the overall map, but from a very specific map where you introduce additional domain language, right? Suppose the embedding then of Theranos became embedded more like Enron versus Apple for a later vintage model, right? Again, so depending on a way a researcher uses a particular model, there is always a way for them to reconstruct some signal which might be correlated with the return that they don't want to correlate with inappropriate information, depending on how they set up the model, right? So overall, what I'm trying to say is that it's awesome that the authors have reduced the models. I spent a lot of time talking about the kind of broader picture, but I'd really want to emphasize that I think it's a really cool engineering contribution. I'd kind of encourage the authors to have a little bit more detail on the data pipeline. I'll send these more details to the authors afterward. But let me just conclude, right? So this is great progress with LLMs and time subscripts. It has recent pre-training data, which the other time subscript models do not yet. And it has better language performance on benchmarks than its peers, which is great for better language understanding. And by releasing these to the public, the community can now use these models with their appropriate data cutoffs to avoid the potential for look-ahead bias. I think my two sets of comments to the authors are, and again, one thing that I also want to commend the authors on is showing that you can actually address look-ahead bias by changing the model. So two things I want to emphasize to the authors. One is to make a little bit more clear in which cases the claims about look-ahead bias potential apply. I think, as a community, we're trying to figure this out, and the more explicitness we have about kind of which test works for which guarantee under which assumptions, I think the better we'll do in understanding kind of the overall potential of the bias. And two, I think, again, the engineering contribution of this paper is very important and interesting. And I think it would help to have a little bit more information on kind of the ways the models were built. But let me just say, I think it's amazing that the authors have trained these models, released them to the research community. I think that I'm very optimistic about our ability to kind of continue on this engineering bent, right? Foundation model providers are not always targeted to the things that economists need or financial researchers need, but we don't have to be consumers. We can be producers as these authors are, and it's a very promising future direction for work. Thank you.
Great. Well, thank you so much, Suproteem, for this fantastic discussion. Asaf, do you want to take just a couple of very brief minutes to respond before we go to the general Q&A?
Oh, I would just take it to thank Suproteem for a very thoughtful discussion. I think we agree on everything you said, and I think I tried to emphasize this several times that our results about look-ahead bias being modest is application dependent. I guess one thought that I had as you were presenting these really nice graphs on the space with the embeddings and the model later is that there's a point we make in the paper, which is that maybe we should make that bigger, which is that the prediction model that you layer on top of the embeddings, if you think about what's the goal of that model, what is the researcher trying to do with that model? The researcher is trying to construct a model that generalizes out of sample. The look-ahead bias from their perspective is a nuisance, right? It's a problem for them. And I think using roughly the same techniques that we use in any machine learning, just sample splits and picking models that generalize well out of sample can correct for some of that bias. Or at least I'm hopeful that we can, and I can't see why we would not. So I don't know how you're thinking about that, but I don't know. I guess I'm more hopeful that that we can address look-ahead bias in many settings. But I would never claim, and I don't think we make this statement in the paper, that look-ahead bias is not a problem. In fact, we encourage researchers to use these models and to evaluate, in their own domains, in their own research space, where they are domain experts. So thanks for the great comments.
Thanks for an amazing paper.
Thank you so much. We now have time for questions from the audience. I think Songrun has already answered a number of them in the chat. So, but if you have sort of more questions, please submit them, and then I'll call on you to get them answered. So I'll call on Bernd. Do you want to just unmute yourself and ask the question, or should I just read it to the audience? I'll read it. So Bernd Woodman is asking a couple of very simple questions. Can you talk just a little bit about the data set? What exactly is being done when you say we aggregate all news articles, headlines for stock in a given day? Also, does the data set provide the headlines by ticker? Also, please speak to the regression a little bit more. What's the embedding vector dimension, etc.?
So Sangro, do you want to unmute and explain how the news return prediction exercise works exactly?
Yeah, sure. So for the news return prediction, we mainly use the Dow Jones newswire data, and so that's a real-time newswire available to most institutional investors, and so it has a very precisely timestamp when the news is available to the market. So that's for that part. We mainly use that data for return prediction.
I would add, you asked about aggregate. That means if you think about the average firm or large firm in particular, say Microsoft, it has many news on it on any single day. So you have to somehow aggregate this to a one day news that you match to returns, and that's the aggregate that we do. We basically take all of the headlines about Microsoft in a particular day and concatenate them into a single piece of text that we then feed to the LLM. That's what aggregating there means. I hope that's clear.
I think Marcus also has a question. Do you want to go ahead?
Yeah, thank you so much for the great presentation and discussion. So I have a question which was partially touched upon, but in general, when you think about any kind of forecasting or model estimation, you have a bias variance trade-off. Now, lower variance from using more data, and there's a problem with the bias here. We have a specific bias, namely the Lookahead bias in Suproteem. Thanks for defining and also mathematically how we should understand that. And then usually you could go and say, well, how can I optimally trade off bias variance? Because I think Asaf's point was in a very specific application exercise, you don't get a lot of look-ahead bias. Therefore, you could actually reduce the variance a lot by using a lot of data in some sense. I mean, that's the way how I interpret it, right? I'm just wondering if you have more to comment about how to think about this bias variance trade-off in a more general way. I think like your work, the second paper that you briefly mentioned might go into this direction, right? How to use more data while still trying to think about bias reduction problems.
Well, I like this idea, and we should explore this much more in the current paper. The other paper, perhaps because I spend a minute on it. The other paper is not really about using more data, but rather using, well, I guess it is in a way. It's about using the largest LLMs, right? The state-of-the-art LLMs possible. And maybe that's what you mean by using more data for their training. But that paper is all about sort of masking or eliminating the lookahead bias from the text to which you apply the LLM. But I think your comment applies to both, right? This is in a way a good way of thinking about that trade-off, and we should think about that more.
In a simple context, in a highly stylized model, I have a prediction model. I impose some structure. I can actually give you formulas of how to think about a look-ahead bias versus variance trade-off. You can use all the data, and you can do some form of bias correction. Again, you need a lot of structure to derive this kind of stuff. And then you get a predictive model with low variance and with some control on the look-ahead bias. And I completely understand in the case of large language models, there's no easy way to do this kind of correction after you have estimated the full model. But I mean, my point is just, it would be interesting to think more along the lines of trading these two things off. And I believe maybe in the context of a specific application, that's the way I interpret your results. You kind of can test this. If you have a very specific application, you can just see how much look-ahead bias you get by using different information sets for training models. And that kind of gives a very crude way of doing that kind of trade-off.
I totally agree with that. If you have ideas about what is that structure we should be imposing, I'd be happy to hear your thoughts on that. In the entity neutering paper, what we did was to define look-ahead bias was to take there's a great paper, theory paper by Ludwig Molinatan and I forget the last co-author. I'll ask for his forgiveness later. But where they they come up with an econometric framework for how to think about a concept that they call training leakage, which is related, not exactly the same as Lookahead bias, but very, very similar, brother, I would say, of Lookahead bias. And what we can do is we can, use that econometric framework to think about Lookahead bias as a sort of problem in generalization ability of the LLM. Like, that there's this LLM and the data set that it was trained on is kind of a black box. You don't know what it is, what's in there, and you have to form priors and you use them about what do you think is or is not in there. And what we show is that if you make what we think are fairly reasonable assumptions on what the neutering model does to the raw text, then you can come up with empirical bounds on look-ahead bias by making these comparisons between the performance of your prediction model on the raw text versus the performance of your prediction model on the anonymized or masked text. But you're completely right. This requires more assumptions. This is not something that you can just do out of the box without more assumptions. But that's life for an econometrician, I think.
Yeah, but I mean, just one idea. So I also did work on variance versus look-ahead bias trade-offs. But one very naive idea is if you have a model trained with all the data and you have a ChronoBERT model trained, I guess you could identify the bias by look-ahead bias by looking at the difference between the two. If you assume under some assumptions that they kind of estimate the same stuff, there's variance around it, but essentially whatever makes these two models different, and there's a lot of assumptions going in, might be related to some form of, you get a log-ahead bias, and then you can try to remove it. It's much easier to think about a simple prediction task to think about subtracting a bias. It's more complicated here, obviously, but maybe there's a way to do this to identify bias, to then use all the data and you take the bias out and you get the best of two worlds. But it requires definitely more thought to do that.
I agree that doing more of these exercises where you go or fix the data or fix the knowledge cutoff and change the application or do the other thing. I think we need a lot of these exercises, right? But the reason I don't know, I was trying to be careful. I hope I was in the way I described what we did, but the exercise where we look at different vintage models does not allow us to completely identify look-ahead bias because there's different knowledge, right? That's playing around there. But we should do more on that. Thank you for the comments. These are great.
Thank you so much. I think, almost all of the questions more or less have been taken care of in direct answers. So I think I want to take this opportunity again to thank our speakers, Asaf and Suproteem, for a very, very interesting presentation and discussion. And before we head to the unrecorded part of our discussion, I want to advertise our next webinar on May 29th, which is going to feature Michael Weber from Chicago booth, who's going to talk about ChatGPT and corporate policies, and Alejandro Lopez Lira from the University of Florida is going to be the discussant, and we're looking forward to seeing many of you there. So thanks again, and a big round of virtual applause, and we'll please stay on Zoom while we upgrade everyone to be a panelist.